I've been diving deep into Kafka lately, and it's honestly one of those technologies that just clicked for me once I really understood what problem it's solving. I mean, when I first heard about it, I was like, okay, another message queue, right? But it's so much more than that. And I think the best way to really get it is through this example I came across. Imagine you're building a website for the World Cup, and you need to handle real time updates for every goal, every substitution, every booking across hundreds of games happening simultaneously. At first, you think, no problem, just put events in a simple queue, have a producer drop events in there when they happen, and have a consumer rad them out to update your website. But then suddenly FIFA decides to expand from 48 teams to 1,000 teams, and they're all playing at the same time. Boom. Your single server holding that queue is completely overwhelmed. So naturally, you do what we always do in system design: scale horizontally, add more servers. But now you've got a new problem, and this is where it gets interesting. If you're randomly distributing events across these servers, you'll end up with total chaos. Goals happening before the match even starts. Players getting booked for fouls in games they're not even playing in. The solution is partitioning by game, so all events from the Brazil versus Argentina match go to one queue. All events from the France match go to another. This way, you maintain order within each game, which is what actually matters. And this is the fundamental insight behind Kafka. To scale, you need a user-specified distribution strategy. You need to choose how to partition your data. But then you hit another wall. Your consumer can't keep up with all these events coming from multiple queues. So you add more consumers, but now you've got consumers potentially reading the same event twice. And your website shows Argentina scoring 2 goals when they only scored 1. That's where consumer groups come in. Kafka guarantees that each event is only processed by one consumer in the group. And finally, when FIFA decides to add basketball to this hypothetical World Cup, you don't want basketball events cluttering up your soccer website, so you introduce topics, logical groupings that let consumers subscribe to exactly what they need. What I find fascinating is that this linear progression of problems and solutions basically leads you to the entire Kafka architecture. You've got brokers, which are just servers holding these queues, partitions, which are the actual append-only log files on disk, topics, which are logical groupings of partitions, producers that write messages specifying both the topic and a partition key, and consumers that subscribe to topics. And the partition key, man, this is so crucial. When a message comes in with a key, Kafka hashes that key and uses modulo arithmetic to determine exactly which partition it goes to. It's deterministic, so all messages with the same key always go to the same partition, which is how you maintain ordering for related events. The life cycle of a message is actually pretty elegant when you think about it. A producer creates a message with a key, value, timestamp, and some headers, sends it to a topic. Kafka figures out which partition based on that hash function, routes it to the right broker, appends it to that append-only log with an offset, and then consumers read by specifying the last offset they've seen. If a consumer crashes, no problem. It periodically commits its offset back to Kafka, so it can pick up exactly where it left off. Now, when should you actually use Kafka in a system design interview? I've been thinking about this a lot, and there are really 2 main scenarios. First, anywhere you'd use a traditional message queue, like when processing can be asynchronous. Think YouTube video transcoding, where you upload a video, store it in S3, then put a message on Kafka with the video ID and S3 URL for workers to transcode into different resolutions. or when you need in-order processing, like Ticketmaster's waiting queue where you want to let people off the queue in groups to prevent everyone fighting for the same seats at once. Or when you want to decouple producers and consumers so they can scale independently. Imagine a leak code competition where thousands of users submit code simultaneously. You can scale your submission servers horizontally, put everything on Kafka, then have just a few expensive workers actually running the code. The second scenario is when you need stream processing, processing a lot of data in real time. Like an ad click aggregator where every ad click goes to Kafka, and something like Flink is consuming in real time to give advertisers instant metrics. Or pub sub scenarios like Facebook Live comments, where one comment gets published to Kafka and multiple servers subscribe to that stream, push the comment to all users watching that live video. But here's where it gets really interesting for interviews, the deep dives. If you mention Kafka in your design, your interviewer is probably going to drill down, and there are 5 main areas they'll focus on. Scalability is the big one. You need to know that a single broker can handle about a terabyte of data and 10,000 messages per second. But more importantly, you need to choose your partition key wisely. I see people mess this up all the time by putting entire video blobs in Kafka messages instead of just S3 URLs. Keep messages under a megabyte. And hot partitions are a real problem. Like if Nike launches a LeBron ad and suddenly one partition is overwhelmed with clicks, you can handle this by removing the key entirely for random distribution, using compound keys like add ID random number, or implementing back pressure. Fault tolerance is another area they'll probe. Kafka has strong durability guarantees through leader-follower replication, and you can configure this with settings like ACKs, how many followers need to acknowledge before moving on, and replication factor. The trade-off is always durability versus performance. When consumers go down, they just pick up from their last committed offset. But timing when you commit that offset is crucial, only after you've completely finished processing that message. Error handling gets interesting because Kafka doesn't support consumer retries out of the box like AWS SQS does. The common pattern is using retry topics. If processing fails, put the message on a retry topic, and after n failures, move it to a dead letter queue for manual inspection. For performance optimization, you can batch messages and compress them in the producer, but the biggest impact always comes back to that partition key choice. You want even distribution across all partitions for maximum parallelism. And finally, retention policies. By default, Kafka keeps messages for 7 days or until the log hits 1 gigabyte, whichever comes first. You can configure this per topic, but be mindful of storage costs and performance impacts if you need longer retention. What really strikes me about Kafka is how it elegantly solves these scaling problems that seem insurmountable at first. The fact that 80% of Fortune 100 companies use it tells you something. It's not just another message queue, it's this robust platform that can handle both traditional messaging patterns and real-time stream processing. And honestly, once you understand the core concepts, brokers, partitions, topics, partition keys, consumer groups, everything else just builds on top of that foundation logically. It's one of those technologies where the more you learn about it, the more you appreciate how well designed it is for the problems it's trying to solve.